Newton's first law of motion. Before Galileo and Sir Isaac Newton's great discoveries, many people thought objects slowed down due to having a natural built-in tendency to do so. But those individuals were not taking in consideration the many forces, such as gravity and air resistance, here on Earth that cause objects to change its velocity. They concluded that the loss of velocity of an object experienced was due to the object's lazy. But as known, that is not the case. Galileo and Sir Isaac Newton came to a conclusion that objects experience a net force, a concept called inertia, and an external force that has an effect on the object's velocity. Recap. As learned in Chapter 3.1, a force is a push or pull exerted by one object by another object or a person. This can be an individual applying a force onto a box in order for it to move. When calculating and addressing forces, it is important to remember that forces are measured in newtons. 1 newton is composed of 1 kilogram times mass per second squared. Whether an object be resting on a table or in motion, a force is always acting on it at all times. This can range from gravitational, tension, friction, applied, and a normal force. External force. An external force is a force originating from outside an object rather than a force internal to an object. For instance, the force of gravity that is exerted to an object on Earth is an external force as it is pushing it to the ground. An internal force is a force acting within an object system. This can be the force of tension and a reaction force. Net force. A net force is the sum of all forces acting on an object. The net force can be zero or have a value greater than zero. The net force, as we know, can be in the opposite direction. Inertia. Inertia is the property of matter by which it continues in its existing state of rest or uniform motion in a straight line unless an external force is applied to the object in order to change its motion. An object that is at rest will prefer to stay at rest unless an applied force acts upon that object. The same goes for an object in motion. An object in motion will want to stay in motion and still travel in that direction unless a force is acted upon the object to stop it. For instance, an object on a table will continue to be stationary on the table unless someone applies a force in order for it to move. Mass. When talking about inertia, it is important to remember that inertia depends on the object's mass. If an object weighs less, it will have less inertia. If the object has more mass, there will be more inertia. To simplify it, an object that weighs more will want to stay in the motion they are currently in, greater than an object with less mass will. This also means that an applied force will need to be greater for an object with more mass. From this understanding, we can conclude that an object inertia is directly proportional to its mass. An example is as follows. If an individual has two buckets, the one on the left is empty and the one shown on the right is filled with sand, which one will have a greater inertia? Since we know that both objects are at rest and want to stay at rest, an implied force is needed to be applied in order for the objects to start moving. Since more force is required to move the bucket with sand, it can be concluded that the heavier object will have a greater inertia since mass and inertia are directly proportional to one another. Newton's first law. Galileo's discovery of an object's inertia is what led to Sir Isaac Newton's creation of the three laws of motion. Sir Isaac Newton's first law of motion states that an object will remain at rest or continue to move at a constant velocity when the net force of the object is zero. This is the case when all forces acting on the object are balanced out in all directions. Balanced forces. The term balanced forces refer to when two forces acting on an object equal in size but act in the opposite direction. This is the case where an object will experience a net force of zero. As seen in the top picture, two teams are pulling at opposite ends of the rope with the same amount of force but in different directions. This causes the forces to cancel out and the students to not accelerate or move. Free body diagrams. Exhibiting two objects' free body diagrams. The diagram to the left shows the forces acting on an object that is at rest. It displays a net force of zero as all forces are cancelled out. Looking at the diagram to the right, it displays an object that is in constant motion. Similar to an object at rest, the forces are imbalanced in all directions, giving the object a net force of zero. It can be concluded that these two diagrams are the exact same, and without any more information about the objects, it can be determined that if an object is at rest or moving at a constant velocity unless told otherwise. Further understanding. Since we know in order for Newton's law to be true, an object forces must be balanced. Since we know the forces are balanced, that means in both cases, at rest or in motion, the net force must be zero. The velocity of an object at rest is zero, and for an object in motion, it is one set value the entire time the object is moving. Therefore, we can conclude in both cases that the acceleration of the object is zero, since no net force is present causing the object to speed up or slow down. Important implications. Some implications can be drawn from this concept. A few things to remember are a non-zero net force will change the velocity of an object. The velocity can change in magnitude, direction, or both. A net force is not required to maintain the velocity of an object. External forces are required to change the motion of an object, and internal forces have no effect on the motion of an object. These are all important implications that should be taken in consideration when solving questions and/or explaining your answer. Applying Newton's law to real-life examples. Newton's first law can be observed in real-life examples. In addition to the use of the law when answering moving object questions illustrated on a free body diagram, Newton's first law is essential to the reasoning behind the implementation of seatbelts and headrests in vehicles. Seatbelt. For instance, the knowledge behind the reasoning of the seatbelt is solely based on Newton's first law. As the car is proceeding forward, our bodies are also proceeding forward at the same velocity and direction the car is going. Our body's inertia is in constant motion the same way the car is. Newton's law states that an object experiencing constant velocity will continue to do so unless an external force is acted upon the object. The external force in this example is the seatbelt. The seatbelt is designed to act as the external force on our bodies to prevent us from continuing to exhibit a constant inertia in the forward direction while the car comes to a sudden stop. This is because our bodies do not recognize the car has stopped and wants to continue in the direction and constant velocity it was once at. This is why it is very important to wear your seatbelt when in a motorized vehicle to prevent any individual from going through the windshield of the car. Headrest. A headrest is found at the back of every car seat. It is adjustable to the individual's height to align with their neck and head. This addition to the car is important to prevent an individual from experiencing whiplash when the car is rear-ended. Consider the forces acting on a person's body during a collision. During a rear-end incident, the car will suddenly accelerate forward and so will your body because the seat exerts a force directly forward onto your torso. According to Newton's first law, your head will continue to remain at rest. Your head will initially snap backwards relative to your body as it accelerates forward since there is no external force being applied to the individual's head causing whiplash. This is the reason for the invention of the headrest, to apply an external force in order to prevent an individual's head from snapping backwards. Testing knowledge. To test your understanding on the following concepts learned today, here are a few application questions that incorporate the concept of inertia and Newton's first law. Question 1. A space probe is drifting to the right with constant velocity in the deep interstellar space, far from any influence due to planets and stars. If a rocket thrust turns on and then off for a short burst of force in the direction shown, what would best represent the path traveled by the rocket after the thrust turns off? Solution. The correct answer is C. After the rocket thrust turns off, there will be no net force on the space probe. Once the net force is zero, the velocity, both magnitude and direction, must be constant. Because of Newton's first law, the space probe must move in a straight line at a constant speed. The fact that there was a vertical force on the space probe does not affect the horizontal velocity of the space probe. It only changes the vertical velocity. A constant vertical and horizontal velocity yields a diagonal straight line through space. Question 2. Runner 1 has a mass of 78 kilograms and is at rest. Runner 2 has a mass of 50 kilograms and is moving slowly at a constant velocity. Runner 3 has a mass of 40 kilograms and is moving quickly at a constant velocity. A. Which runner will experience the greater net force? Explain. B. Which runner has the greater inertia? Explain. Solution. A. The correct answer is none. All the runners have a net force of zero because according to Newton's first law, an object at rest or at constant velocity will have a net force of zero. All runners are either at rest or in a constant velocity, resulting in all runners to have a net force of zero. B. Since we know the mass is directly proportional to the object inertia, it can be concluded that the runner with the mass of 78 kilograms has a greater inertia since they have a greater mass out of all three runners. Since we know mass is directly proportional to inertia, the greater the mass, the greater the inertia. Question 3. Describe what happens to an individual if they are riding a skateboard and the two front wheels hit a curb. Solution. Your body will keep moving forward and fly off your skateboard since the curb only stops the board, not yourself. This is because, as we know, our body travels at the same velocity as the skateboard would in this example. Since the skateboard is stopped by the curb, our bodies do not recognize this and still continues forward. Since there is no external force being applied to stop the individual from continuing forward, they will end up accelerating forward until they hit the ground. Summary. In summary, inertia is a property of matter by which it continues in its existing state of rest or uniform motion in a straight line unless that state is changed by an external force. An object at rest wants to stay at rest, and the same goes for an object at a constant speed. An object inertia is directly proportional to the object's mass, concluding that the heavier the object, the more inertia it has. Newton's first law expands off of Galileo's concept of inertia. Newton states that an object at rest or experiencing at constant velocity will have a net force of zero, therefore balance forces in all directions. This leads the object to have no acceleration and stay in motion or at rest until an external force acts upon it. Lastly, the concept of inertia in Newton's law is used all around us, and most importantly for the safety of individuals in a vehicle. In conclusion, Galileo and Newton both helped individuals in the world grasp a better understanding of an object's movement by developing the concept of inertia and Newton's first law. Galileo's concept of inertia is what allowed Newton to create his three laws of motion that are used in everyday life. Both of these concepts are found and applied in today's world. Through an understanding of the law of inertia, it is able to develop the practical applications for the prevention of injuries in vehicles and invent more safer technology as a whole.